today's lesson is a real number is nothing but an infinite word in the modular group. But an infinite word in the generators L and S of the modular group. So, but I'm going to express this in an even more fancier way, and I'm going to say that the boundary of the modular group, or which amounts to the same, is the boundary of F. It is R plus infinity. And this in a very natural way. So, okay, first of all, we define an end. This construction can be carried out for an arbitrary tree. So let F be tree. We define an end of this tree is an equivalence class of infinite non-back tracking paths in F. Modular equivalence where two paths are equivalent if they eventually coincide. So what does this definition mean? We have to draw a graph to see it. Okay, here we have a small portion of the tree.
Do you have a base point?
No, you don't need a base point to define ends. If you start from a base point, then if they eventually coincide, then they coincide all the time. This relation becomes meaningless. Okay, so
the same intersection is infinite.
yes.
So then we need less words because eventually this is.
This has something to do with the topology as well. So perhaps it is better to keep it. So for example, let's consider this path, which starts here. So it is not. So we don't consider bi-infinite paths, just infinite paths. So we consider from somewhere and go to infinity, I don't know, like this. And I could start from here, and follow the same track as the first path from some point on. So if I call this gamma, and if I call this gamma prime, then gamma and gamma prime they define the same time.
No, the start point has to be a final point.
Yes, we don't consider bi-infinite paths, just final paths. It is natural to, there's a natural extension of this story to such paths. But for the moment, we just consider one-ended infinite paths. So now we want to introduce a topology. In order to introduce a topology, for the moment, the boundary, okay, the set of paths is denoted del F, and it's called the boundary of F. But for the moment, this is just a set. If you say boundary, well, that means a sort of compactification. Which is a compactification? There's a way to see this tree as a topological space, which is not compact. You can imagine that we are adding some points to this space by in order to compactify it. So, okay. In order to put a topology on the set of ends, I need a base point. So I choose a base point. Let's say this. I could choose it here. Then, since this is a tree, it is simply connected. In every class of ends, so each end is a class. So in the class of every end, there is the unique representative which starts from this base edge. Let's call this E. So we introduce a topology, choose a base edge, and identify this set of ends by the set of infinite paths of F which start at E. So these two sets are in bijection.
What is E of F?
It's a base edge.
No, big E of big F.
The set of edges of F.
The set of it out.
F is a graph and capital E of F is a set of edges. Well, how can I identify? For example, this is one class, right? These two belong to the same. These two determine the same end, so they belong to the same equivalence class. But in this equivalence class, there is a unique path, which is this one, which starts at E. So let's call this gamma double prime. So gamma double prime is a representative. So this gives us this one-to-one correspondence. And then I can put a topology on this space by declaring that two paths are close if they go together for a long time. So what does this mean? So, for example, one neighborhood of gamma. Okay, now I don't have this anymore. I just consider the path starting here. So one neighborhood of this would be the set of paths which go together until here, and then all paths from this point on. Okay. Smaller neighborhood is the set of paths which coincide with this path until here, and then all paths, all possible continuations. I hope this is clear. So this is in fact the usual topology, usual product topology. Well, okay, let me draw something so that it becomes much clearer. So let's say that tree is something like this. And suppose that I have some path. Okay, so one neighborhood of this consists of all paths which start at E, which follow the same track as our gamma, and then from this point on, you have all possible paths. Okay, this is one neighborhood. If you want to take a closer, smaller neighborhood, you go with gamma one step more, for example, till here, and then you consider all possible continuations of this path. So this set of paths ends gives you a closer neighborhood, smaller neighborhood, and so on. Gives us a neighborhood base. And the topology we obtain is the topology of the counter. But it is obviously not the real, so I have to do something more. So if R3 is regular, if F is regular, we can consider just one branch like this. So this is the regular tree because all vertices here are of degree 3. Then I can identify this set of paths by, for example, here I always have two choices. Okay, so this is same as I can identify the set of paths, this 0, infinity to the power omega, so all infinite sequence of 0 and 1s. This is, so this gives us with only this portion, but it is almost same as the boundary that of itself. So this gives some identification between these two, and this under the product topology. So the topology that we have on this set is topology of the counter set, or the Teichmüller topology. So we denote this by del E. So what happens if you choose another point, base point, instead of E? We can choose another base point. This gives us another identification of the set of n's with another Helmholtz group, but these two can be identified among themselves. If I choose another set like this, then these two sets are evidently not equal. Okay, they are not the same set. But the topology, there is a one-to-one correspondence passing through here, and which can be described as, I mean, if your second base point is here, then any set, any path to infinity can be obtained by composing some path from E to E prime. So these two are canonical bijection, and this gives us a homeomorphism between these two topological spaces. So if I choose another base point, I obtain another boundary which is homeomorphic to this one. But it is necessary to choose one base point to define the topology. So, in general, if f is locally finite, then this is homeomorphic, just this. To the counter set. Which means that it is totally disconnected. Which means that, in fact, every neighborhood that I described is open and its complement is open also at the same time. So both all sets are closed and open simultaneously. It is compact. Well, it is perfect, which implies that it is also uncountable. And it is not too big, so it is materializable. Topological space, which characterizes complexity. It has no isolated points.
No isolated points.
Now, let us come back to our tree. F with y, part right, Now, since the edges, so every edge of our tree carries the name of an element of the modular group. So since the edges of F are labeled with elements of PSL2 Z, then we can consider that at each infinite word, each infinite path based on the identity element as an infinite word in the generators. So, if I have some gamma which belongs to, now I put my base point on the identity element, then gamma can be described as some infinite word in LMS, which we can write this as ls to the power n naught times l square s to the power n1 l s to the power n2 and so on. Or it may start with s, in which case it must be written as s times ls to the power n0 l square s to the power n1 and so on. Where here n naught is non-negative and I are positive. And if you want me to be more explicit, for example, if this is the identity, then this path, this precise path, first I'm turning left, so it should be left, once more left, and then once more left. So, okay, I turn once left and I go to the other side, so ls, turning once more left, ls, ls, and then here I'm going to be turning right, so I'm going to have l square here to s from here to here to l squared s, and then once more l square s, l squared and so on. This is the way every infinite path is encoded by an infinite word in the modular group. We have one more thing. Modular group PSL2 Z acts on the boundary where I don't care about the base points to start with. It just sends a path to another path. Okay? But then this action gives us an action on the set with boundary and set with a base point. So it acts on this, obviously because they are in one-to-one correspondence, and this continues. This action is continuous by homeomorphisms. And what is the action? We can describe the action as follows. Every element of PSL2Z can be described as a word in LNS exactly in the same manner. So if I have an element like this, N1 and so on, ls to the power mk. Well, this is not the most general form, but so it may start with an s and with an s, I don't know. But this is, some of the elements in here can be written like this. And this element acts on this element simply by writing this to the initial part of the gamma. So if this is this, and then gamma, m gamma is the infinite path ls to the mk times ls and naught and so on. Now, as I said, as I constructed in my previous lecture, this F is not just a tree, it has an additional structure, which is a structure of a ribbon graph. So we have some extra things to say about the tree. So with reference to the structure, there are some paths which are special, which are more special than the other paths. If we consider F as a ribbon graph, and if you are confused about the ribbon graphs, you can just consider planar graph. Then there are some special paths. Those are the paths which turn always left from some point on, or which turn always right from some point on. So they look like as follows. So I have something like this in the tree, like this. So there are branches going on like this, but from some point on, our path is always turning here right, and here it always turns left. So there are such paths. Without the planar structure, if you consider this as an abstract tree, then there is no such notion. It is only thanks to the ribbon structure or the planarity of the graph that we have such a phenomenon. And we are going to call these paths rational ends. And together we are going to call these pairs of rational ends. But now look, these sequences, finite sequences at least, they were encoding ratios. Finite sequences, they encoded ratios. And if I look at this path up until here, then I'm going to have some ratio. And if I look at the corresponding word, I'm going to have something like this. If I have such a path, which always turn left or right from some point on, it is ls, for example, to the power this, and L square s to the power n, and then ls to the power infinity. This is a path which turns always left from some point. But if I look at to which number this should correspond to, by using accessing to the content fractions and one and so on. Okay, this is k plus 1 over n k plus we have 1 over infinity. So we can just imagine that this represents a finite path which starts here. We just consider this to be the 0. So those rational ends, in fact, they represent rational numbers in a natural way. What about the other path? Other path going like this. In fact, the other path corresponds to the other way of representing the same rational number by a continued fraction, which is this. So this number is the same as n1 and n0 plus 1 over n1 plus until 1 over nk, but this time minus 1 plus 1 over 1 plus 1 over infinity. These two are the same. These two denote the same rational number. If we look at its encoding, I'm going to have ls to the power n naught and L square s to the power nk minus 1 times ls times L square s to the power infinity. So if one of the paths like this, one of these paths is encoded this way, the other path is encoded this way. So they represent the same rational number, and what do? We set them equal. We introduce another equals relation. equivalence relation on this set, pairs of rational ends are equal. I mean, to give you a more precise idea of what rational end is, you may consider a path which once goes left and once turns right, once left and once right, like this. So this is an irrational path. In fact, this path corresponds to the golden ratio. So if it stabilizes from some point on, then it is a rational path. So this, what does this equivalence relation do? Its equivalence relations are, equivalence classes are singletons if the path is irrational, if it does not stabilize, and it consists of precisely two paths. These two pairs, this pair of paths, in case it stabilizes from some point on. And what do? We consider the quotient space. So we have an equivalence relation on a topological space, and there is the notion of a quotient topology. We consider this topological space, and we call this S1E. And it is easy to show that first, the action of the modular group here onwards, it preserves the set of rational ends. Why? Because it just puts some word in front of this, so the behavior at infinity is not modified. So the action of the modular group passes here, first of all, on this topological space. Secondly, if I choose another base point, not E, but another base edge, E prime, then the spaces that I'm going to obtain are going to be homeomorphic. In fact, this is going to be a circle. This is going to be a circle. So before I go with something like a proof, proceed with something like a proof, I want to make an important observation about what is going on here. So it is the following observation. So what did we do? We started with some counter topology, and from that counter topology, we ended up with the circle after this quotient relation. So we have some continuous map from here to here, which is canonical. And now, just consider the following thing. So, where's my figure? Okay. So let me consider the modular graph. The most simplest modular graph, in fact, look like this, as you remember. This is the quotient of the tree by the modular group itself. Now, if I consider slightly more complicated modular graphs, I have things like this, for example. This is the next, and this is just an Z square, which uniformizes this. Its Bailey map is just Z square. And I have this. And then I have sometimes I may have loops. For example, this is another modular graph. And here I have holes, punctures. So these are puncture surfaces. Here I have one puncture at infinity. Here also I have one puncture at infinity. Here I have one puncture at infinity. And in between I have more complicated graphs living on surfaces, but also always with some punctures. Okay, there are punctures here and there. And on top I have the tree. Now those, in fact, pairs of rational ends, when I consider those paths which eventually turn left or turn right, you see that those paths are going to the paths which turn around these punctures. So this operation of passing from here to here, in fact corresponds to, in some sense, to filling these punctures. So below, so this operation here is viewed as the operation of filling in the punctures on the level of modular graphs. This must be of significance from several points of view. For example, it is related to the question I asked to Sasha about the possible ways of expressing the same algebraic curve, arithmetic algebraic curve, via dessins. Okay? What do we do? Because here it's a sort of compactification operation. You kind of glue back these points and see what's going on. And why do I call this big crunch? It is a very big collapse. This operation of gluing back these points, in fact, collapses all planar graphs, all planar modular graphs to nothing, to just one point. Okay? Because they just live on the sphere, and from the arithmetic point of view, they are all equivalent. And once I glue the punctures, it is only those punctures which distinguish between them and the graphs. And another significance, it must be of significance from the point of view of mapping class groups as well, although I'm not able to say more about this.
So here, I mean, it's a sphere, it's a boundary of a plane with a different topology. You identify the boundary of a tree with a boundary of the upper plane with a different topology. That's your notation.
No, I didn't identify. There is a function, continuous function, which goes from here to here. This is not a homeomorphism because it's not one-to-one.
Yeah,
it is one-to-one. Huh?
What is the right-hand side? S1E.
Okay, this you may consider to be the boundary of the upper half plane. It is possible. If you consider the canonical realization of the fairy tree as a subset of the hyperbolic plane, as an orbit of that little arc on the boundary of the fundamental domain, then yes, you can say that this is a sort of identification between the boundary of the tree and the boundary of the hyperbolic plane. But it is not an identification because this application is not one-to-one. It is one-to-one on irrational paths, but it is two-to-one on rational paths. So those two paths. So okay, well, if I have to draw you the graph, you have the following phenomena. You have some path like this, and another path like this, and in fact this corresponds to a parabolic element. So you have on the tree, okay, so there are branches that separate everywhere, but you have two paths which converge on the boundary to the same point. And we set them equal, because they tend to the same point. Is it clear?
Okay, so your boundary of the tree is not equal to the boundary of the upper plane. It's not.
Boundary of the upper half plane is a quotient space of the boundary of the tree, and a rather simple quotient space. There's a countable number of points which are identified 2 by 2, and there's an uncountable number of points on which they are identified. Simple identified. Okay. Now what do we do? What do we do? I do the obvious thing. I consider the map. Which goes from this, excuse me, which goes from S1E to R, and which sends the path represented by this, excuse me, LS to the power n naught times L squared S to the power n naught and so on. This to the continued fraction n0 plus 1 over n1 plus 1 over n2 and so on. If the word starts with L, if it doesn't, if it starts with an S, then we define the image to be just S of this. So this is minus 1 over minus 1 over n naught plus n naught and so on. And the theorem is that this is a homeomorphism. This is well defined because the pairs of rational ends are sent to the same point down here. So it is well defined and it is a homeomorphism. Why is it a homeomorphism? Usually you might be obliged to consider the usual topology on the real line, but in fact the idea of proof is much simpler than that. This correspondence between rational paths and rational numbers is 1-to-1. So each rational path is represents a rational number and vice versa. And this is an order preserving in a very precise sense. This is an order preserving identification. Hence, every infinite path is in fact nothing but a Dedekind cut. Okay, it just separates all rational numbers, all pairs of rational numbers into two parts, which respects ordering and so on. So every infinite path is nothing but a Dedekind cut. And the proof simply goes like that. Theorem. We call this continuous fraction map. So continuous fraction map is a homeomorphism. And there is one very nice thing about this identification. We may consider those paths which are eventually periodic. Those are the next simplest paths among all paths. Well, what paths we have? We have rational paths which stabilize eventually. And the next class of simplest paths are those paths which are periodic. So you just take an element of the modular group and you make it periodic. You just repeat and so on. And that gives you a correspondence between under this periodic paths are sent to quadratic irrationality. Okay, and how we can reply this question as follows. This is the second fact. If we just follow up our construction from the start to the end, you'll see that the action of the modular group on this space conjugates to an action of the modular group here, and that action is nothing but the action of the modular group by Möbius transformations. P to Z acts on R on S1 of E, doesn't matter, same thing, because it's homeomorphism, by Möbius transformations. So if you take an element M and make it periodic, it determines you a path, and that path represents precisely a fixed point, one of the fixed points of M, if M is hyperbolic. So you take ax plus b or cx plus d equals x. You write this equation if M is the matrix A, B, C, D. You write this equation, you solve it, and the path which is the periodization of M represents precisely that quadratic number. The other root is the path which simply goes in the other direction. It is M, the periodization of M minus 1. However, one of the facts of nature is that this correspondence cannot be extended to cubic irrationalities, for example. Well, because this question is related to, well, it is the same thing as expressing, for example, the cube root of 2 as a continued fraction. But this cannot be done, and nobody have been successful. People are only able to make some statistics, some conjectures about the statistics of such numbers. They obey the Gauss-Kuzmin statistics and so on. So nothing is wrong about them. But if you consider the problem that I asked in my previous lecture about rectangular regions, comparison of rectangular regions, you may end up with some kind of continued fraction representation of cubic numbers. Some sort of. Okay. So how much time do I have left?
8 minutes.
8 minutes. Okay. So.
So for factor 2, the periodic points always correspond to invention of quadratics. Are you using this classical result Lagrange? Are you giving a new proof? You wrote down the factor, the last one.
Yes.
Okay. How do you prove this?
Like this.
The one above.
This
The
is
one
the
above. Under this correspondence, the periodic passes are sent to quadratic irrationals.
Okay, to prove this, you use this fact, and to prove this, you use this fact.
Okay, so how to prove it?
So you look at the corresponding infinite continued fraction.
Yes.
Okay, if you have something periodic, then the corresponding continued fraction must be periodic. So you have this
So you're using this.
n1 plus 1 over nk and repetition.
Okay.
Okay, now call this number x. So this corresponds to some periodic path, right? So x is same as this number. So I just put x here, and if I just collect everything back, I'm going to obtain x equals ax plus b or cx plus d. So if such a number exists, if this converges, then it must satisfy this equality, and we are done. So, well, I think I have proven my claim in the start of my talk, so I may try to start something new, which is just as, which is not very complicated, but okay. So we are turning back to the Euclidean algorithm. So I gave you two ways of comparing magnitudes. The first one, all in the first comparison process, what we did, we just we compared this until here, and we looked at the remainder. Okay, so remainder. But there's, and then I described the second one, and in that second comparison process, what we did every time we came until here, and once more, and we considered the negative remainder here. Let's say, okay, negative remainder. But as you know, in the Western civilization, we are obsessed with doing things in the most optimized and effective manner. So we may choose alternatively between these two. In every step, we might decide to apply one of these, but whatever one gives us the smallest remainder. So between this remainder and the negative one, we always choose the smallest one. So this gives us another comparison process, which appears to be a little more effective. Okay? So this is the third variation of it. This also gives, so here we end up with continued fractions of the form and note plus minus 1 over n1 plus minus 1 over n2 plus minus nk plus n and so on. Where these signs are determined by the real number itself. You don't know what these signs are from the very start. So in the first application of the Euclidean algorithm, we decided that these would be always pluses. In the second version, these were always minus signs. Now I propose to choose these plus or minus signs as a function of the number itself. In every step, we choose this one or this one, but whichever is the smallest one. Or we may decide to do the other way out. We may decide to pick the greater remainder. That gives us another Euclidean algorithm. In fact, you can, for example, if you want a Euclidean algorithm which exclusively belongs to you, you may just choose an infinite sequence plus minus to the power of omega, and you may say to yourself, I'm going to apply in my algorithm always this sequence of signs, plus, minus, plus. Once positive remainder, once negative remainder. Once positive, one negative, and so on. Okay, this is one possibility. Another possibility, which is even wilder, is that you may decide to choose, you may give some function from reals to here, and you may decide to choose this plus or minus signs as a function of r, as in this case. Here, these signs change as a function of r. For one real number, you get one sequence of signs. For another real number, you get another sequence of signs, if you decide to do the optimal algorithm. So you may introduce your own optimal algorithm with respect to some other criteria by giving some function from here to here. This is not pure speculation. Some people actually do it. There are some ways of choosing via some dynamical systems, for example, ways of choosing these signs as a function of r, and that gives us yet another Euclidean algorithm.
Change your mind continuously.
Okay, well, that's even wilder, okay? Yeah, one day you may try and decide that like this, another day another one. Okay, this is yet another idea. But the point is that now, you see, we started with the simplest Euclidean algorithm, and I gave the sort of canonical interpretation of what that algorithm is. So every application of the algorithm was just a path going to infinity in the tree. But now we have so many possible continued fractions. How shall we interpret them? Okay? And, well, I'm sorry, unfortunately I don't have enough time to explain that, but you can find that in my, the answer in my lectures. You may also interpret them as paths to infinity, not on the modular group, not on the Fourier tree, but on some other space. Thank you very much.
Thank you. Are there any questions?
Do you have a higher dimensional version of the continuous fraction?
Yeah, that is my exercise from last course. So, if you decide to compare not length, but areas of rectangular regions, you are going to have some higher dimensional analog. So you end up with not linear things, but they are branched. They branch all around. You just don't go like this, but you have. Do you understand? So we have 14 fractions like this. So they go in every direction. So if you bifurcate twice in every step, then it is dimension 3. More than dimension goes higher.
And which group does it correspond to?
It does not correspond to a group, it corresponds to an operand. Operands. Here you obtain a modular operand. If you want to generalize the modular group to higher dimensions, it is not a group anymore, it's an operand.
Are there any other questions? No, then let's discuss. We start again at
before you read this, I want to see this. It says MF. Is it from the model? I don't know if I can